Thanks for the introduction. I'm happy to present our work, Virtual Mirrors, Non-Line-of-Sight Imaging Beyond the Third Bounds. And first of all, a small disclaimer, this presentation does not actually contain any nerves. In fact, it's not even neural, but we still think that you will find it pretty cool. Non-line-of-sight imaging methods reconstruct objects that are hidden around the corner. Here, we target this orange object, and we use an ultra-fast laser which shoots a light pulse towards a single point in what we call the relay wall. This illumination is going to scatter and is going to hit the hidden object and later back to the relay wall. Then we use an ultra-fast camera which is able to capture this time-resolved indirect illumination. This is a video of the response to this light pulse. Let's take a look at the path that each of the photons take in this case. First, they touch the relay wall, then the hidden object, and then back to the relay wall. Using these known laser and camera positions, and this time of flight captured by the camera, we are able to triangulate positions of the objects in the hidden scene. By repeating this procedure multiple times, we're able to obtain an image of the whole scene. This is a hard problem, because it requires the analysis of indirect illumination through 3 bounces, and there is very low signal-to-noise ratio. Nevertheless, there have been many good works that attempt to solve this problem. Some of them are even based in nerves and also deep learning. In our work, we are the first ones to tackle a much harder problem, which is looking around 2 corners. So consider this scene from before. So if we add a second occluder here and move the object around it, now this object is hidden around 2 corners. So how can we reconstruct it? Our first observation is that light needs to bounce at least 5 times in order to touch the object and go back to the camera. So we see that this is a much harder problem because it requires accounting for 2 extra bounces and there's even less signal to work with. So, to put our work in context, from this list of works, we are based on the phasor field formulation, which I will go into details just now. It goes in 2 steps. First, in the real domain, it uses the laser and camera, as I explained before, and this data is put into a computer and is transformed in order to build computational imaging devices around the corner. These devices have a virtual line of sight towards the hidden scene and can perform tasks such as illuminating the scene, such as a virtual point light with an arbitrary illumination function, or a virtual camera which is able to capture this illumination and then take a picture of objects in the hidden scene. This virtual camera behaves just like a real camera, so it also has a focus plane. So an important part that you need to know is that the position of this focus plane determines what is seen on the final reconstruction. In this scene, for example, we have an R and a T letter, and the position of the focus plane determines which letter is seen in the final image. We will use this important fact later. So, how can we use this phasor field framework in order to look around 2 corners? Now, I will go into detail into the key observation that enables us to do this application, which are virtual mirror surfaces. First, in the real domain, as I said, we use this laser pulse, which uses nanometer wavelengths in the visible light range. Under this illumination, surfaces behave as diffuse, and light is scattered in all directions. However, our key observation comes that in the computational domain, the virtual point source uses centimeter wavelengths instead, as the capturing system is limited and is not able to capture the phase information required in the nanometer wavelength, but instead captures in the centimeter wavelengths. However, our key observation is that under these centimeter wavelengths, surfaces might exhibit a specular behavior. And in order to understand why, let's zoom in the surface to see why this happens. So at this level of zoom, the illumination is represented as this incoming wavefront, which is now planar with respect to the surface. And as it hits the surface, it's going to create additional secondary wavefronts which propagate spherically over time. The main observation is that the superposition of all of these spherical wavefronts creates a reflected wavefront which propagates in the specular direction. And this is just explained by wave interference and Huygens principles, so it's just basic physics principles. So this is our key observation. We observe that diffuse surfaces can exhibit specular behavior in the computational domain, and we call those surfaces virtual mirrors. So, going back to our question, how can we use this observation to reconstruct objects? We see that the virtual camera is going to observe this surface as a virtual mirror. And just like with real mirrors, we can see objects reflected in the mirror, even if the objects themselves are hidden. So we use this observation to look around 2 corners. Zooming back, we see our setup seen right here with an object hidden around two corners, and we observe that the virtual mirror in this case is going to create a mirror reflection of the hidden object on the other side of the mirror, just like with real mirrors. So to answer our question, in order to look around two corners, what we do is we place the focal plane of the camera and image the reflection of the mirror. Now we can see some results of our procedure. We perform results or experiments in simulated and real setups. Here you can see the object that we are hiding around two corners, and here is the image that we capture on the reflection of the mirror. We also try to rotate the object by 180 degrees and see that our image also rotates by 180 degrees. We also perform experiments in real setups with real capture hardware, where we hide different objects around two corners, such as nothing, or a rectangle, or a T-shaped object, or an inverse T, and we see that we have a reasonable reconstruction of the shape of the object. And keep in mind that this image has been computed with light that has bounced 5 times in diffuse surfaces, looking around two corners. So it's a pretty hard problem. And one of the good things about our observation is that I explained it using the phasor field formulation, but our theory can also extend to other non-line of sight imaging algorithms using our same virtual mirrors theory. So until now, I talked about one of the applications of virtual mirrors, such as looking around two corners, but in our paper, we also tackle the missing cone problem, which is a fundamental problem for non-line of sight imaging, and I will go into details just now. So consider a scene right here where we have this imaging setup with 3 surfaces, G1, G2, and G3. So the missing cone problem refers to the fact that some of these surfaces cannot be reconstructed depending on their position or orientation. So if we naively try to image these surfaces around the corner, we see that only G1 and G2 are visible, but not G3. Virtual mirrors offers an intuitive explanation of why this happens. We see that light going from the virtual point source reflects specularly on the surface and goes to the camera. The same goes for the second surface. But the important part is that the third surface reflects light specularly away from the camera because of all this virtual specular behavior. So this is the explanation for the missing cone using the phasor field framework and our virtual mirrors theory, but the same problem also happens for other non-line of sight imaging reconstruction algorithms. In our work, we use this scene to tackle the missing cone problem and try to image a surface that previously could not be reconstructed. So we have this scene with 2 surfaces, M1 and G1. And if we try to naively image these surfaces, we only see M1 but not G1. And as explained previously, this is because light is reflected specularly away from the camera. However, we observe that even if the third bounce doesn't reach the virtual camera, higher order bounces might eventually reach this camera. So how can we use this fourth bounce illumination in order to image this surface? Our key idea is that we build a second virtual camera located at this hidden surface instead of at the virtual wall, at the relay wall, sorry. And this camera is able to use this third bounce illumination in order to construct an image using the same principles as I explained before. You can find more details in our paper, or you can ask us later. But as you can see here, this second virtual camera is able to obtain a good image of an object that previously was affected by the missing cone. Finally, to talk about some limitations, the first one is that virtual mirrors are not perfectly specular. This specular behavior is not perfect. And we can see here in the 2-corner setup that I explained previously, the captured image appears a bit blurry. And this is because the virtual mirror, we are imaging the reflection, but this mirror is not perfectly specular. If we compare it with respect to the single-corner setup, where we place the physical object at the position of the mirror reflection, you can see that the image is a bit clearer. Also, our novel imaging method has similar artifacts to what's already existing in third bounce methods. From the example I showed before, if we try to image this whole area, we see that this image contains multiple things. The first one is the surface that I showed you previously, which is good, but this illumination captures both the third bounce, fourth bounce, fifth bounce illumination, and all this information is entangled. So all these reconstruction methods have these kinds of artifacts because they can disentangle this multiple bounce information. In conclusion, we have shown applications for 2 outstanding endless imaging problems, which is looking around 2 corners and the missing cone problem. And all of this is based in the fact that diffuse surfaces can exhibit specular behavior in the computational endless imaging domain. We call these surfaces virtual mirrors, and we use this to understand the behavior of the virtual camera, such as understanding the missing cone, and to extend the current third bounce imaging methods with the applications that I showed you. That was everything. If you want to check our project page, you can scan this QR code. And if you want to ask any questions, I'll be happy to answer them later. Thank you.